Okay, we got treats in here.
We are up and running whenever you're ready.
We'll wait 1 more minute. That clock says 1 minute to 12. So what's the official Apple time? What's Apple time?
I've got 12 noon.
Oh, okay. I guess we'll get going. Okay, welcome everybody to our seminar. It's a great honor and an immense pleasure to introduce today's seminar speaker, my dear colleague and friend, Dr. Seraphine Hauser. Sarah is at the end of a one-year postdoctoral visit here at the University of Wisconsin, arranged under the auspices of a grant authored by Dave Parsons and Stephen Cavall at the University of Oklahoma. Directed toward better understanding forecast errors as well as developing artificial intelligence tools to explore them. Sarah spent a few weeks in Madison in the summer of 22, is that right?
22, yeah.
Yeah, summer of 22, while finishing her PhD work under Christian Gomes at KIT, the Karlsruhe Institute of Technology in Germany. She fell in love with Madison, and by a magic that is still under investigation, was able to convince Dave and Stephen that she should spend 2024 in Madison instead of Norman, Oklahoma, which was, of course, a coup. We're immensely glad that she did that. Sarah is an expert in large-scale cyclone dynamics, blocking the structure and evolution and dynamics of large-scale weather regimes, which, as it turns out, have a considerable influence on forecast success. And she's been particularly interested this year in the nature of major forecast busts, especially at the medium range of about 6 days. And I'm not going to let the cat out of the bag of her results, but I will say that they are both encouraging for the entire NWP enterprise, I think you'd agree, and simultaneously full of avenues for new research, certainly sufficient to fill a decade or more of productive science in the near future, and for me, thus ensuring the viability of synoptic dynamic meteorology into another generation. So I'm really excited about that. But easily, the worst part of our jobs here at the university as scholars is seeing our colleagues depart, either after they graduate or upon finding exciting new positions. And for Sarah, it's the latter. She is going to be taking up a new extended postdoctoral position at ETH in Zurich under the legendary Heine Bergman. And it is the lab for synoptic dynamic meteorology in Europe. And Sarah's comprehensive excellence is what earned her such a coveted spot. So I'm sad to see you go. However, I'm already looking forward to an afternoon on the sidewalks of Zurich in the near future, sharing a coffee or tea or whatever else might come along. So I'm looking forward to that. And without further ado, my dear friend, Seraphine Hauser. And she's going to tell us about characteristics of large-scale circulation forecast busts over Europe in the ERA 5 reforecasts. Sarah.
Yeah, thank you, John. Thanks so much for introducing me. And yeah, I'm happy to tell you a bit more about my project that I've been working on in the last 12 months here. You can read the title. It's about characteristics of large-scale circulation forecast busts over Europe in ERA 5 reforecasts. But I will get to those different key points in a minute and tell you a bit more about what I actually did. So because this is a bit of a longer talk, I wanted to show you a brief outline, just that you know what to expect in the next half an hour. First, I want to introduce you to predictability and what forecast busts are. And then I will tell you more about what I did in the last 12 months. So I looked at different forecast bust definitions and tried to see if we have to revise them or extend them. We talk about the occurrence and seasonality of those exceptionally poor forecasts and also compared to exceptionally good forecasts. And then we take a perspective into the patterns that are linked to very bad and very poor forecasts. And then in the end, we use weather regimes to get more information about the variability of those events. And that is followed by a summary and some next steps. So first, part A, the introduction to predictability and forecast busts. So first of all, we got pretty good in weather forecasting in the last years. So what I want to show you here on this figure, this is from the European Center for Medium Range Weather Forecast. And it shows kind of a compact perspective on the Northern Hemisphere in the extratropics and tells you about to which forecast lead time we can deliver skillful predictions. So this is shown on the y-axis. So this is the forecast day until we have valuable predictions and forecasts. And here on the x-axis, you can see the years that range from 1998 to 2024. So what you can see in the blue line, this is a monthly mean of like the forecast day that we can predict to, and here a smooth line, this is the red one, just gives you a bit more a smoother perspective. But what we can see if we just like compare both ends of this time range. So in 1998, we were just able to predict the mean until forecast day 5. Well, in 2024, we are able to predict until nearly forecast day 7. So we gained 2 full days in predictability. So we see like the steady improve in the predictability of the large-scale circulation in the extratropics. Another way to show it is when we look at different forecast lead times. So we can look at the day 3 in the forecast world, day 5, day 7, and day 10. And now see, when we look at the forecast accuracy, so the higher the value, the better the forecast. We can see that also with time, so we have again here the years, with time we get more and more skill for those different lead times. And this increase in skill with time is probably due to improvements in the weather model, but also more in qualitatively better observations. But however, we sometimes struggle still, and I think everyone is aware of that. So sometimes global numerical weather prediction systems produce significant drops in the accuracy of their forecasts. And how does that look like? It's shown here on the left-hand side on this figure. So again, we have here the forecast accuracy ranging between minus 100 and plus 100. So 100% is the perfect forecast. The smaller the value, the worse it is. What you see here is a period in March and April 2011, and every line here shows you the forecast accuracy for a different weather model. For example, the red one is the European model. We have the UK Met Office model in blue, the Japanese model in black, the Canadian model in orange, and in green our NSAP model from the US. And what we can see is that the model performs quite well in terms of the forecast, and here we forecast the accuracy over Europe at forecast day 6. So this is a period where nearly all the models have a good skill. But however, you can see the sudden drop that nearly all the models have. And these are often called, like these events where you have those sudden drops are often referred to as forecast busts. So these are large forecast errors. And here in our study, we use the definition of significant drops in the large-scale forecast scale at forecast lead time 6 days over Europe. I wanted to show you a bit more about previous research on forecast busts to understand it a bit more, so what has been done in the past. And the first kickoff study was by Mark Rodwell et al. From UW-AOS. And what they did is that they first systematically investigated large-scale forecast busts over Europe based on 2 criteria using the Z500 field at forecast day 6. So they used 2 different definitions. The first one is an anomaly correlation coefficient that gives you an idea if the forecast field is in line with the analysis field. If it's not in line and if you have like a phase shift, then this value drops below a certain threshold. And so here they set this threshold of 0.4, and this is kind of the first criterion for a forecast bust. The second one is the mean squared error. If that is passing a certain threshold, then we have a significant amplitude error in our pattern, and those 2 combined make like the full definition of forecast bust. So what they did in their study is that they looked at operational forecasts for a 20-year period and also reforecasts in blue, and looked at the number of those forecast bust events as a function of the time. And here you see the period from 1989 to 2011. So what they found is that in the operational forecast, they found like a decrease in the number of forecast busts, while for the era interim, the decrease is still kind of visible, but not as strong as in the operations. What they then did is that they looked at different patterns to understand more what could be reasons for those forecast busts. So they first systematically investigated the patterns of those forecast busts, and I wanted to show you those composites here. So here on the left-hand side, we see for the initial time the Z500 composite, and you can see different features here that kind of they pointed to. For example, here this red field shows you positive geopotential height anomalies over the Canadian region that they refer to as the Canada high, and other features are, for example, the Rockies trough here with negative geopotential height anomalies. They also looked at Cape at initial time, and they found positive Cape anomalies over North America, which they refer to as the North America Cape region. And there's a hypothesis that convection in this region is able to trigger forecast busts over Europe 6 days later. And then for day 60, they presented the other pattern, where they showed that there's a blocking over Northern Europe, shown by this red contours, like the positive geopotential height anomalies, and you also see signals of anticyclonic Rossby wave break. So 4 years after this kickoff study, Vito and Parsons in 2017 worked more on the variability of those forecast bus and did a more recent systematic analysis based on error interim reforecasts. I tried to summarize 3 of their main results. So here on the left side, you can see that they did some kind of a clustering to explore the high seasonal variability within a data set of forecast busts. They also looked at tropical cyclones and found that recurring tropical cyclones can kind of have an effect on predictability over Europe, so this plays a role too. And another thing was that they looked at different error patterns, and they showed an existence of a Rossby wave train upstream of Europe that kind of propagates an existing error into the European region. There's some further studies, and I just wanted to summarize them very quickly here. So first of all, there are a lot of studies on the diagnostics for error development understanding, more the questions of like, where do the errors develop? Can we focus more on those regions, and can we track those errors? So there have been a lot of error tracking methods, but they have only been applied to forecast bus cases. And another thing is that there is a link of initial errors to strong diabatic heating. So massive scale convector systems, mostly here over the US, you can see just like one error here that is introduced due to one of them. But also like subsynoptic scale moist processes linked to one conveyor belts can trigger forecast busts over Europe. All right, some open questions that we still have. What about forecast busts in other like data sets than the ones that have been used in the past? What if we have a longer data set, longer than just the 20 years that we have? Are there any trends in the data sets and also in the annual bust frequency? What can we also learn from a comparison when we look at those exceptionally poor forecasts, when we look at exceptionally good forecasts? Because we often focus just on what's going wrong, but what if we just compare to things that are going pretty right? Can we also further understand the variability between those cases? There has been studies trying to do that, but it's still not 100% clear. And also, what should have happened between the initial time and day 6, and what went actually wrong in the cases of the forecast bus. So in the second part of my presentation, we finally go into the research part that I've conducted in the last 12 months, and we look at the revision and also at the extension of the forecast bus definition. So first of all, I mentioned this before, reforecasts, but what are reforecasts? So reforecasts are pretty much weather or climate predictions that are made for past events using modern forecasting models. So forecasting model is applied to historical data. We often refer to them as retrospective forecasts, or often also hindcasts. And I try to just like give you an explanation what is the difference to our actually operational forecasts, which are just behind our weather apps and everything. So what we see here are 2 timelines. For the upper row, for the operational forecast, you can see different plots. These are different model versions. So we have a model version, then model adjustments are made, and we get hopefully better forecasts. And this happens for the European Center at least once a year, sometimes twice. But you have steady like model improvements and adjustments. Reforecasts use the same model version. So we take a pretty modern model, but run it for historical data. This is the major difference. So why do we use the reforecast? Well, we have consistent retrospective predictions over a very long period, because we can just like apply to historical data using the same model configuration. And therefore we can use that for model performance evaluation, because the model adjustments and improvements do not play a role because we keep the same model. All right, so in this study, we use ERA 5 reforecast from the European Center. It's 45 years of deterministic 10-day forecasts based on the constant model version, in this case, the IFS cycle 41R2. We have data for the Northern Hemisphere, 1 degree spatial resolution in latitude and longitude. We have twice daily initial time, so the model runs at 0 and 12 UTC. And to compare the forecast, we take the ERA 5 reanalysis as our true state. So we can now take the original definition of forecast bus that I presented before by Mark Rodwell and al. In 2013. So they had those two criterion with the anomaly correlation coefficient and a root mean squared error. And now you can see here on the right-hand side of this figure, this is a scatter plot of the ACC and a root mean square error, so just like two skill scores. And every point here points to one of those reforecasts. So in total, we have 32,000 reforecasts. And if we look at the different thresholds, these are the points in this box who fulfill both of those conditions. And in our case, for the whole data set, only 2% would be referred to as forecast bus. So what we are doing now, because we also want to adjust it to our new data set, but also extend it to exceptionally good forecast, we work on a novel definition of forecast bus. So what we want to do as well is that we're looking for a combined index, also based on the ACC and a root mean squared error. So it's kind of, we rely on the same skill scores. But a major change here is that the root mean squared error is deseasonalized. This has a reason because we have a seasonal cycle in the root mean squared error. So what we do is that we remove the climatology and divide it by the standard deviation. In the next step, we normalize both scores that they are defined between 0 and 1. And with that, we get a really good correlation between two skill scores, which is pretty good. It's 0.78. And then in the end, we define a combined index with a different weighting. We could have gone for like 0.5 times ACC plus 0.5 times root mean squared error, so that both of them would have had the same weight, but we decided to put more weight on the ACC because we're more interested in the cases that have like a huge phase error than an amplitude error, because timing is often more important than the actual strength. So what we then did is, when we defined the combined index here, that is based on ACC and root mean squared error, we can then look at our poor forecast, so the forecast bus, by taking the 5% with the worst combined index. And this is now the extension, because we also want to look at the good forecast. We can also look at the 5% with the best combined index. And now we can see on this scatter again, we have still the ACC here. Now we have the standardized root mean square error here. And now we color the points, the forecast, that fulfill those conditions. You can see we have like the very poor forecasts here. So they have a low ACC and a high error. And we have the exceptionally good forecast in this area. All right, let's now look into the occurrence and also the seasonality of exceptionally poor and good forecasts. First of all, I wanted to show you what would have happened if we would have taken this Rodwell criteria from the old data set and applied to our data set. So what you see here on the y-axis is the rate of poor forecasts in percent, and here's now our timeline. In the gray lines, you can see the data set that previous studies have used. It's shorter, it's just like 20 years or a bit more. And what you can see is if we apply the same criteria as for them, for our data set, and this is the black line, you can see we end up with a much lower rate of poor forecasts between when we compare it to the ERA interim base reforecast. So in this case, that means the ERA 5, like the reanalysis data set that the reforecast data set that we have, shows a better performance than the old one. This is another reason why we use our combined score, and now you can see the rate based on our combined score in this red line, and you can see it's the best of both worlds. It's not as low as as using the old criteria, but it's definitely just like the best of both worlds, I would say. And when we now compare like the rate of poor forecast between like earlier years here in the 80s and 90s to like where we are right now, you can see that there's a decrease in the number of forecast busts with time. And this is really interesting because that means we experience less forecast busts than a couple of years ago. We can do the same for the exceptionally good forecast, and it's not surprising that we see a very different behavior and just like in the end the opposite behavior. So looking at the green line, which shows you the rate of good forecast, you can see we have an upward trend or an increase in the frequency of exceptionally good forecast. And this is mainly due to the fact that we have more and also better observations that get into the model. We can now look at the seasonality and see if they occur more in the wintertime or in the summertime. So if we look at the pool forecast, and now we look at the fraction of pool forecasts here, and every bar stands for 1 month, you can see that there's a peak here in the summertime from June to October, so into the late summertime. And this is, we think it's mostly linked to summertime convection and also to the North Atlantic hurricane season. While for the good forecast, we have a really reverse picture. You see the highest bars are in the winter month from like October to March. So this is where we have the peak occurrence in the cold season. And here we think it's related to low frequency modes, just like the El Niño Southern Oscillation, but also the Madden-Julian Oscillation, where we can gain a lot of skill from. All right, let's jump to the next part. So we looked at the occurrence, frequency, but also into the seasonality. But how do the patterns look like, and is there a lot of variability here? So first of all, we want to do composites, same as the ones that I introduced in the introduction part. And first we look at the pool forecast. We look at day 0, this is shown here, for the pool forecast, and we look again at set 500 to get like an idea of what the wave pattern looks like. And yeah, we can see the same features that also previous studies have seen. So we see the rocky stuff here and those negative geopotential height anomalies. We see kind of a Canada high. It's more towards higher latitude. It's more like an Arctic high, but it's kind of like really similar features that we find here, although we look at a different model and a different data set. We can also look again here at the Cape composite. This is also again at day 0. And here we see again positive Cape anomalies in the North American Cape region. So this also goes aligned with what previous studies found. And then in the end, this is shown on that side. We can look at the pattern. So this is just day 0 and this is day 6. So this is 6 days later. And we see that we have a pronounced pattern here over Europe and also over the North Atlantic, just upstream of the box. With positive geopotential height anomalies more over northwestern Europe, and here negative geopotential height anomalies more towards Iceland. However, let's compare it now to exceptionally good forecasts. And we can definitely see there are strong differences in the patterns. First, if we look at day 0, we can see, we don't see like the wave pattern we've seen before here that goes back to the date line over the North Pacific. We don't see a wave pattern in the exceptionally good forecast. But what we can see is like an established pattern that ranges upstream to the US-American continent with like positive geopotential height anomalies that are really pronounced here over Northern Europe and also going through Central Asia. Very interesting, we don't find those positive Cape anomalies here over the North American Cape region, also a strong difference. And if we look at day 6, we can see a pretty similar pattern to what we've seen at day 0. So it seems like the large-scale pattern seems not to have changed quite a lot. But what I can take away here is there's a very high variability in those composites. So it's really interesting what happens now between initial time and day 6, and how can we measure this kind of variability. And this brings me to the last part. This is part E, where we look at it from a weather regime perspective. So what are weather regimes? Weather regimes are persistent, recurrent, and quasi-stationary flow patterns of the large-scale exotropical atmospheric circulation. And they're really useful to describe the large-scale circulation and respective changes in a specific region in a really compact way. So what I want to try to explain you here is that we look at cyclonic regimes and anticyclonic regimes. Cyclonic regimes are dominated by cyclonic features. In that case, you can see this low pressure system here. This is a typical positive NAO phase where we have like strong winds here. I think it kind of points a bit to the surface weather that you would experience if you would be here in Europe. But the main part is that you have like a dominant cyclonic feature, which is the low pressure here. On the other hand, if you look at anticyclonic regimes, they're often linked to high pressure systems, and they dominate large scale flow. And in this case, if you would have like a high pressure system located here over like Sweden, Norway, you would experience in summer a lot of like, sunshine. And those different regimes are really helpful to predict the surface weather, but they can also be used to investigate variability. So what do we use here? We use a year-round definition of North Atlantic European weather regimes. This is by Gramsada from 2017. And what we basically do is that we take set 500 anomalies and perform an EOF analysis and subsequent k-means clustering, and then end up with 7 different circulation regimes. And they are illustrated here on the right-hand side. So 7 regimes, 3 of them are cyclonic, so they are dominated by a cyclonic feature that are shown here in negative geopotential height anomalies. So we have the Atlantic Trough, the zonal regime, and the Scandinavian Trough. And then we have for anticyclonic, or often referred to as block regimes, which are the Atlantic Ridge, the European blocking, the Scandinavian blocking, and finally the Greenland blocking. And what we use here to condense all this information is a weather regime index. And this one is used to assign every time step to one of the 7 regimes. It's kind of a projection of an actual field to one of those 7 regimes. So using this, we can gain a lot of information about the variability in our cases. So what I'm showing here, and this is now for only the pool forecast, is on the left-hand side. These are the number of forecast bus cases. These are the different months, the different seasons. So we have the wintertime with DJF here, the summertime with JJA. You can see the peak occurrence in summertime again, as I told you before. And you can see that all the different colors, so every color is one of the regimes, you can see that you find them in all seasons. So there's not like a really specific pattern here, but you can also see that there are a lot of times where you have this gray color, and this gray color is when you cannot assign your circulation to one of the 7 regimes. We can look at it from like a weather regime frequency anomaly perspective, and then understand how anomalous it is that forecast paths occur with one of those regimes. And you can see that there's a lot of gray in like this positive region, which means that the initialization of pool forecast anomalously often is linked to none of the 7 regimes. And this means at the time where we initialize the forecast that end up being really bad, we have a highly transient flow. On the other hand, we can look at the good forecasts. We can see here the maximum in the wintertime again, the minimum in the summertime. And looking at the weather regime frequency anomalies, we see that there's less no regime cases, so the gray bars are now negative. And mostly we have good forecasts that are initialized when one of the 7 regimes is active. And also if you look at the summertime, you see like this huge signal of the Scandinavian blocking, which is something that seems to be really interesting. So in the next step, because we just looked at the day 0, so just at the initial time, there are 2 ways to look at the next 6 days. So first of all, we can look at the reanalysis and ask ourselves, okay, what should have happened? Or we can look in the forecast and ask ourselves what happened in the forecast run, which was probably different from the reanalysis run. So today I will just focus on the first question, but I give you more information towards the outlook. So the first case is that the regime at the day 0 is still the same regime at day 6. So this means the large-scale circulation does not change heavily. And this is in 35% for the poor forecast and in 37% for the good forecast the case. We can look at the different regimes and if they, the ones that don't have any transition. And what we can see is, because we see a lot of high gray bars, is that the model struggles to predict the continuity of a no regime phase for the poor forecast. Also for the winter time, we see 2 peaks here in red and in blue, and they show the 2 NAO-linked regimes with the Greenland blocking and the zonal regimes. And here it seems like the model cannot predict persistent NAO phases. We can switch to the other side, to the good forecast, and we can see that there is a dominance of the Scandinavian blocking. So this is the green bar, so there's a specific dominance from one of the regimes in the different seasons for good forecasts. But we can also see that the Greenland blocking in winter shows this persistence too. Now when we look at the second case, this is now when the regime at day 0 is not the same regime at day 6. So there must have happened like a regime transition. And this is for like most cases what's happening. So it's like 65% for the poor forecast, 63% for the good forecast. And what we use here to get more an idea what actually happened is we use a transition matrix that shows you, this is like the transition from to transition to. So it shows you from which regime something transitions in the following regime. And the colors point to like frequencies, and you can see that there are high frequencies here along the edges of this matrix. And that easily means that the transitions from or into the null regimes, are the ones that are really frequent during full forecast. So the model struggles to predict like the onset of a regime, but also when a regime decays. For the good forecast, you can see it performs surprisingly well with the onsets of block regime or transitions between block regimes. So one example is from the null regime here to the European blocking or the Scandinavian blocking. And previous literature suggested that blocking onset is something that models really struggle with. So this is really surprising. And because it was so surprising, we were wondering, does the timing of the regime transition within those 6 days, does that matter? So what you see here in this figure, it shows you the regime transition frequency on the y-axis. On the x-axis, you see the time around forecast initial time. So this is where our forecast starts. This is where it ends. These are the days around it. And if you now focus on those thick solid lines in green and in red, so the green ones for the good forecast, the red ones for the poor forecast, you can see that their timing is kind of shifted. So you have an early peak in good forecast, meaning that most good forecasts show a transition earlier in the lead time. Well, for the red line, you can see the peak is later in the forecast time. So the transitions occur later during poor forecast, which is something the model can struggle with the further it gets away from the initial time. We can look at those dashed lines. These are now just the cases that have one regime transition, and you can see it's kind of the same signal. So like early transitions for the good forecast, later transitions for the poor forecast, just a bit of a higher frequency. And alternatively, if no regime transition occurs, we can see that there's a peak in the regime transition just before that time or immediately afterwards. So what we kind of conclude from here is that the timing really matters. And this brings me to part F, where I talk a bit about summarizing points and some last steps, since the year is nearly over. There's not a lot of time left. But yeah, summary, what did we do? So we revised the definition of large-scale forecast bust and extended it to exceptionally good forecasts in the 45-year period of era 5 reforecasts. The 4 key findings are: we find a decreasing number of poor forecasts with time and an increasing number of good forecasts, despite no changes in the model physics. And this is then probably due to the observations that are improved and more frequent and just probably better. Second point, we found a high agreement in the large-scale patterns at initial time of forecast bust between era interim and era 5 busts, indicating struggles that are independent of the model version. So just to remind you, we found features like the Rockies trough and the Canadian high. And then the third point, we find very clear differences in the seasonality and also in the patterns. When we talked about seasonality, I hope you remember that the poor forecasts are more frequent in summer and the good forecasts are more frequent in the winter. And then in the end, and this is the fourth point, we looked at the weather regime perspective and found some similar characteristics between good and poor forecasts, but also differences in certain regime transitions and different regime types, and particularly in the timing of those transitions. So talking a bit the work in progress, one thing that I'm working on right now is to apply the regime perspective to the forecast data to actually find like an answer to the questions: are forecast busts also regime busts? And the first quick look showed that around 55% of all the forecast busts over Europe could occur with regime busts in the North Atlantic European sector. And a small to do here is, are there problems in predicting a long-lived regime continuation or a specific regime transition, so to really compare what happens in the forecast. And also, what is the reason for correct regime predictions during European forecast busts? And one of the answers is it's a different domain. So imagine you have those two different regimes. So the European blocking that has like a dominant feature in our Europe box here in the black box. So that matters more than if we look, for example, at cases where the arrows might be here linked to Greenland blocking, so over Greenland, but are not in the box. So this could play a role here. And the second part of work in progress is, can we predict the occurrence of exceptionally poor and good forecasts using AI? So this is the AI part of this work, where we trained a convolutional neural network. So we used fields at initial time, so at day 0, fields like the set 500, mean sea level pressure, K, also day of the year because there is a seasonality. And we try to predict if this AI model can tell us, just based on the initial time, if this forecast is going to be good or poor. And we had some first success in the prediction of forecast skill. So what we did is that we defined different classes of forecast skill. So class 1 is very poor forecast, class 5 is very good forecast. And this is a confusion matrix. So what it actually would tell you if the model would be perfect is that you just like see very high values here in the diagonal. But of course the model is not perfect, so you don't see that. But you can see kind of that there are darker colors towards the diagonal, which means we have some skill. So this is something we're working on right now to improve this model, and then also to look into the decision of the model based on which fields and features it makes those decisions. And with that, I'm at the end. Thank you for your attention. If you have any questions or comments, I'd be very happy to hear some. Thank you.
Questions. We often begin our questions with student questions. Patrick.
Is there a way to assess if the model's physics or initialization are going wrong, or if it's random chance that's creating these forecast busts? Do you know? Is there a way to separate the two?
Oh, you mean if initial time is, like, if at initial time there are also some errors that are introduced that early?
Yeah, and if it's the model, or is it something else that's going wrong, creating these forecast busts?
I think because the model is initialized based on error 5 reanalysis, and it has more observations at that time, because it's like you can take all the historical data. At initial time, like, the error is 0. It's just that the errors, they come up during like the first 3 lead times, like lead days. I mean, this is something that a lot of people look at, but it's probably like really micro scale processes, synoptic scale processes that can trigger those events, probably. Yeah, that's something.
Hamish.
There's a way of decreasing busts through time over the last like 30 years.
Mm-hmm.
And you said it was observations, and that's a pretty, like, it seems bold that observations are linearly improving the forecast. I wonder if you have any idea of like what observations that could be that contribute directly to forecast busts.
I think what was really surprising, and you can see it the best if you look at the rate of pretty good forecasts, you can see that jump, and like the rate of exceptionally good forecasts. And I talked with people at the European Center and told them that I find like this jump in the rate of good forecasts. And what is really interesting is that they use a lot more satellite data from the 2000s on, and using that data really improved the models.
That's when Madison and Apple were launched.
Yeah, that's interesting, huh?
A lot of that.
Yeah.
Yes, Ian.
I had a clarification question about the very end, your future work. You were relating, you said 55% of the time there was a regime bust over the North Atlantic, and there was a, maybe I just missed it, but could you clarify what a regime bust is? Does that just mean that they couldn't classify the regime, just the North Atlantic regime, or region?
Exactly. So what we do to kind of condense the information is that we project like fields at a specific time into those 7 regimes, and if they show like a high projection into one of those regimes, we assign them to the regime. If that is not the case, if the pattern is not similar to any of those 7 regimes, then it's classified as the null regime, and we do that in the reanalysis world, and then do it in the reforecast world. And regime busts in that case would be if the regime at day 6 in the forecast is not the same as in the reanalysis.
So the regime is calculated over a region of the North Atlantic, or over the entire Northern Hemisphere?
The regimes are defined like in this is the EOF region. It's the North Atlantic European sector. This is where we define the regimes. but we define a forecast bus just over this European region. So we think that I was quite surprised because I thought if we really look at exceptionally poor forecasts, then the regimes must be wrong too. But what if like the arrows are not as large upstream and get the regime, especially a regime like the green unblocking in this period here, or in this area here, right? But then high arrows are in the European region. So this is kind of what we think could be the case.
Got it, thank you. I think I just misunderstood the regime. So when if you're in European blocking, that's the regime for the entire North Atlantic and European sectors.
Yeah.
So you're saying that 55% of the time, we're actually not in any known regime, but we busted the forecast over the small box.
I wouldn't say that at 55% we are not in the same regime because, yeah, sometimes we have like this null regime that counts also as like a regime. So, yeah.
Cool, thank you.
Sure.
Any other questions? Jerry?
So I'm not a semantics person, so I have a really basic question about the definition of a bus.
Mm-hmm.
So why is Z500 used as a variable to define a bus? And then also, do we use the day 6 forecast because that's the kind of firm limit that we're at with predictability?
So to your first question, we use Z500 because we look at large-scale circulation bus. I mean, depending on what kind of forecast bus you want to look at. Like, you could also look at precipitation bus or temperature bus, but large-scale circulation bus is kind of a good way to go because we can kind of get an idea once we know the large-scale circulation. We get kind of an idea of the temperature and also like surface weather just based on the circulation pattern. So this is why we use Z500 here, but you can basically just do it with different values or different fields and variables too. Day 6, that's kind of a funny story because I was surprised too, why do people choose day 6? So I talked with people at the European Center and they just said they decided at some point to look at day 6. So yeah. I think you can do it also like, if you want, you can also look at forecast bus in like go further out of the medium range and go more to like the sub-seasonal range. This is also what a lot of people do. But yeah, it's a good question, yeah.
Yeah, Daryl's question inspired one for me. Could it be that the seasonality in the busts is associated with the definition that you're using? So since you bust more often in summertime and this part of your domain would look particularly tropical in like most of summer, then perhaps, you know, the relationship is based on using the 500 hectopascal, which would be better in the wintertime anyways?
I mean, you have a lot of freedom in defining what you would count as a bust in the end. What we try to do is to not remove the full seasonality. I mean, if you would deseasonalize the ACC too, then you would end up with like a really even number for the different months. But we kind of wanted to keep the seasonality. It's like one of the main results, and we made sure to deseasonalize the mean squared error, that we don't have that effect, because yeah, as I said, there's like a high seasonality in the mean squared error. But still, it's not like a pure seasonality question, I guess. Yeah. But in the end, there's like a lot of freedom how to define buffs. Some people would only use the ACC or only use the mean squared error. So I think it depends on if you're more interested in an amplitude error or in the phase error.
Any other questions? Yeah.
When we define your index, given the weights, say from A to CC and 0.2, looks like a little bit subjective. So if there's any reason why you think, why did you get, why do you give that weight for that?
Oh, you mean the 80% ACC?
Yeah.
I think it's a good question.
Why not all the values?
So when I started this project, I thought more about defining busts just based on the ACC, because both skills are highly correlated. So if I just go with one of the skill scores, I'm really likely to end up with also high root mean squared errors, just like automatically. But in the end, I just went like a step back and tried to investigate more. Are we more interested, like what is worse, having a phase error in the pattern or having an amplitude error? Like in phase error could be just the timing of a specific pattern to happen. An amplitude error is more like how strong will it be? And I think based on that, I kind of adjusted my weights a bit and was like, okay, we are really interested in those situations where the phase error is really bad. And a root mean squared error is just like making sure that we take care of the seasonality of it. I think this is kind of what we try to balance between. But changing that to like 0.7 and 0.3 doesn't change a lot in like the cases that we select. So this is good. It's kind of still pretty robust, I would say.
Any other questions? Okay, I get to ask one. Stephanie, you had your hand up. I couldn't see you on that slide.
Go ahead.
Okay. This is interesting on so many levels to me, as you know. I think there's some really interesting analogies that are coming to my head, and some of them are really stupid, but the background regime stability is an interesting question. How volatile are some of these regimes? You know, one of the things that Maria did, which is really interesting about the JET self-organizing maps, was once we found those 12 patterns, it was really fun and interesting, just on a fundamental phenomenological level, to kind of investigate what's the longest lived SOM 1 event, SOM 2 event, and so on.
Yeah.
And they're wildly different. Some of them can last 42 straight days, some of them never last more than 6 days. I wonder if the same kind of analysis somewhere in the regime work has been done. It probably has. But do you have an idea of which of these regimes, just independently of anything else, last the longest, and therefore one could come away wondering if they aren't the least perturbable regimes? Because I'm thinking the weather systems that come along have the ability to nudge these things into a different space.
Yeah.
And if you have a fairly perturbable regime, then weather system developments can really push it away.
Yeah.
But if you have a really robust and unperturbable regime, then it might not matter what weather systems come along within it to kind of nudge it. It won't get nudged.
Yeah.
Is that part of what might be going on here?
I think so, and I think I see some signals in some of the analysis, like just like go back to one of those ones.
Yeah, this would be a perfect place to entertain this question, yeah.
I think in my opinion, it makes perfectly sense that we are often in a no regime, like really often in a no regime.
Yeah.
Where you have a highly transient flow and the model really struggles to see if any large-scale pattern that will be stationary and persistent kind of builds up. That
Yeah.
makes much sense to me.
Yeah.
For the good forecasts, I mean, you don't see like this bluish colors here in the frequency anomalies, but green unblocking is like a regime in the winter time that is really persistent and can last up to like a month or something. Same with Scandinavian blocking in summer, like when you have the typical high latitude blocking situation in summer, that's also a regime that is really long lasting.
Yeah, so, okay, that prompts another question, if you don't mind, Sarah. Has this analysis been divided into seasons, cold and warm season?
Oh yeah, this is like DJF, like these are...
Oh, sorry, it already is, yeah, okay.
Yeah.
And so,
So that's kind of a signal what you can, for example, here see in summer with like a lot of Scandinavian.
okay, that's
So
already
if you
there.
have this persistent regime and you just like initialize during such a long-lived regime,
Yeah.
then you will end up 6 days later with the same regime. So just predicting the persistence.
Yeah, and a collection of
It's
weather
really
systems that
successful.
might be spawned within a regime might be well absorbed by that regime, and those systems support its, its continuity
Yeah.
in some instances and not in others, and that maybe is at the heart of some of the question here. And if you start out with a no regime, anything goes. It's the Wild West. You can initialize, plant seeds for anything that comes next, and there's no way in 6 days you're going to have the same forecast skill.
Exactly, and
Yeah.
for example, also, if you have good forecasts over Europe, it doesn't mean you don't have arrows upstream over the North Atlantic. You
Yeah.
have like cyclones hitting just
Yeah.
like upstream of that block.
Yeah. Can I throw one last question?
Sure.
It relates somewhat to Ian's question. The big North Atlantic, the big Western Hemisphere for the regimes, and then on the eastern side of that domain, the European place where you're measuring the errors. What if you take the European place and put it over on the western side of that domain, and you do the same analysis? So are there forecast busts along the east coast of North America
That
precede forecast busts in Europe?
I mean, I haven't done exactly that analysis that you suggest, but what I did was an error perspective. You just like see the error growth within those 6 days and see if the error grows somewhere else.
Mm-hmm.
And we selected a lot of different boxes. We selected the North Atlantic, we selected USA, Canada region, Eastern, Western, North Pacific, Central Asia, just to make sure to see where do errors pop up and where do they grow the largest. And what we find is that errors grow largest before day 6 over the North Atlantic, so upstream of Europe, but also in the high latitudes in the Arctic.
Very interesting. Okay, and hence Nurture and all the other field programs. Okay.
Exactly.
Very cool. Thank you very much.
I was wondering, with regards to the no regime cases, do you have a sense for how much of that is transient versus not a regime that, because it's based on POF analysis, right? So there's going to be orthogonality restraints between each regime that have to be orthogonal to each other. But there could be patterns in there that can persist, that have memory, beyond just transient features, but they don't fit the orthogonality restraints of an UF analysis. So I'm wondering if how much of that is actually transient versus just doesn't meet the criteria of the regimes?
That's a good question. And that's something that I wanted to look into in the future, because we found a lot of no regime cases for the co-forecasts. We need to look into that and see what's actually happening. If we cannot assign it to one of the 7 regimes, what does it look like? How high is the variability within those all no regime cases? Maybe we even find a pattern just looking at those no regime cases. So yeah, that could be really interesting. Maybe also something to go with, because in the forecast where we just assign the regimes now, it's kind of the same. We see a lot of times where the model misses then to go into the regime, or it goes out from the regime and transitions into the no-regime. So really understanding this onset and decay, what happens with a large scale is kind of key, I guess. Thank you. Same?
That was fabulous, thank you. For your AI work, beyond what you've done so far, what plans do you have to do after?
I think one part that I would like to do, maybe I just jump back to this one. I think this whole analysis looking at exceptionally poor and exceptionally good forecasts and seeing in the composites we find differences in the signals, that kind of triggered the whole AI idea of what if we just give the model those initial conditions, and then probably the AI model sees, oh, Rockies trough, oh, Canada high. This is going to be a pretty bad forecast. And I think that was kind of the motivation. The model is trained. I continuously train the model, change something. I'm still thinking about different variables, what makes sense. But if we end up with a pretty good skill, I think it's interesting to go more to the explainable AI side and be oh, okay, why did this model decide to predict the skill class? And then seeing that it picks up features like this, or features oh, we have high K values in this region, that would be ideal, because then it kind of confirms our hypothesis with that study. So that could be
What data are you using for training?
For training, I pretty much use this forecast data and the reanalysis data for validation. So I think in terms of data, I think with the 45 years, it's a good database that we're having. But I fear that we might not be able to get better skill in our model because the variability is so high between those cases that even the CNN might struggle at some point. picking up those equations.
Any other questions or comments? Jared?
Would you say we need more observations to reduce the forecast bust, or like what do you think we need to do?
I think the more observations we have, and if they're also like qualitatively good, the better. The better is like the kind of starting point for a model. So I guess I mean the decline in the poor forecast that we see with time is probably like linked to those observations that are feeding into the model. So
Can you use your results to target where you think we need more observations, or is that not something you can really do?
I'm not sure. We can use that. But I think like measurements campaigns such as like the Nordic campaign and the things that are planned for the North Atlantic will be also really useful, because when we have those measurement campaigns, we suddenly have so much more observations, and seeing if we use that data for data assimilation for the models and see if we get higher skills in a time that would probably not be skillful, that could just like push more this hypothesis how important like, those observations are.
Yeah, and it strikes me, I don't know if you're thinking this way, Jerry, but it strikes me that dissecting some of the really bad forecast busts, at 12-hour intervals, and seeing where, and this goes back to one of the questions you had, I think, in the back of your mind, Patrick, where does it start to diverge? And then what are the features that are forcing the divergence, as your expert judgment allows you to make a guess? And then you could maybe start to say, geez, they always seem to emerge out of the archipelago, or something like that over Canada, and then you have some idea of where you might target. But I don't think you could do it without that kind of work.
I think so. I mean, what is interesting, I see signals that things diverge a lot from forecast day 3 on. It's not day 1 or day 2, but the only thing is also I'm looking at like the mid-troposphere.
Yeah.
And mostly I would guess you would have arrows like close to the surface.
Or tropopause.
Or tropopause,
either way
especially
you're missing it.
tropopause.
Yeah.
And until they propagate like vertically, it just takes a bit of time. So this is probably why I think we see arrows popping up at day 3 and not earlier.
And they cook slowly too. Slight changes in the advection along the jet core, for instance, changes the whole complexion of the trough at 3 days compared to what might actually turn out.
Yeah. So I think it's like a really open field of people trying to use arrow diagnostics to see from like which levels are the arrows coming from and how long does it take until they propagate vertically.
Yeah. Interesting. Okay, we've kind of reached the hour. Unless there's a final comment, this has been a great question session. Sarah, thanks for putting up with it. And thanks for an excellent presentation. Join me.